Hi everyone. Postgres stores data on disk in 8 KB chunks called pages. Every time we insert a row, Postgres needs to find a page with enough free space to fit that row. It's fine when your table is small, but a 100 GB table has around 13 million pages. And each page's free space keeps on changing as new rows are inserted or older ones are deleted. So how does Postgres quickly find the page to insert the row? That's what we are covering today, the data structure that makes Postgres inserts fast, the free space map. Let's put together what's our wish list for this data structure. The first thing that we want is to be able to search and update the free space. Before inserting a tuple, we want to search for a page with enough free space, and after an insert is done, we want to update the free space of that page. Both of these operations need to be fast. By fast, we mean something like O of log n. The second thing that we want is to check the maximum free space available across all the pages. Think about why we need this. If the maximum free space across all the pages is sufficient, only then do we do the actual search operation. Otherwise, we should immediately return and create a new empty page. So this operation of finding maximum has to be immediate, which means in constant time. The last item on our wish list is a bit nuanced. When we are inserting data, we don't want all our inserts going to the same page. We want our inserts to be more or less uniformly distributed across all pages. Let's take an example to see what this means. Let's say we have a brute force approach of iterating over all the pages till we find enough free space. Let's say we are doing 3 inserts and the page 3 has a lot of free space. So what will happen here is that the algorithm will return page 3 for the first insert. It will return the same page 3 for the second and third insert also. So all our inserts went into the same page. This isn't ideal for performance. Ideally, if there is enough free space in several pages, then we would want to spread the inserts across these pages. So ideally, we would have wanted one insert to go to this page 3, the second insert to go to this page 4, and the last insert to go to this page 5. So these are the 3 things. We want search and update in log n time. We want to find maximum free space in constant time, and we want to distribute the inserts evenly. Now there is one data structure that we know and that we can use for this, and that's the Max-Heap. We can have a Max-Heap where all the leaf nodes store the free space for the pages, and the internal nodes are just the maximum of the child nodes. With this, we can find the maximum free space immediately because it's just the value of the root node, and the search and update operations are also O of log n. So the first 2 items on our wish list are already being taken care of. Now we just need to find a way to distribute the inserts. One easy way of doing this is to implement a round robin based search. For instance, let's say we call the search operation once and it returns the second leaf node, which is to say that this node had enough free space. Then the next call to the search operation should start at this next node and continue the search to the right. And if we reach the end, then the search should wrap around. That's what round robin search means. Now notice what we are saying here. We are saying that the search operation should start from a leaf node, not the root. And we have to remember the node from where we should start the next search operation. Let's see how this is implemented. So at a high level, the search will be implemented in 2 phases. First, we climb right and up till we find a node that has more free space than what we want. Then once we have found such a node, then we consider this node as the root and descend down like we usually do in a heap. This step of moving towards the right and up helps us ensure the round robin search. Let's do one quick dry run here to see how this works. Initially, the leaf node to start the search is this 0th node. We'll keep a variable called as next slot to track the node index from where the search should start. We'll keep a variable called as next slot to track the node index from where the search should start. I'm going to abbreviate it as ns. So at first, ns is equals to 0. And let's say that the search method gets called with a required size of 8. So as per the algorithm, the first step is to climb right and up until we find a node with enough free space. So we first check if this current node has enough free space. Here it doesn't. So we need to go to the right sibling and then to its parent. Now this node has the free space that we want. So we are done with the first step of the algorithm. Now as per the second step, we have to consider this node as the root and search as we would in a regular heap. Here clearly the left child doesn't have enough free space, so we descend to the right child. And since this node here is a leaf node, we have found the page with enough free space and we can stop the algorithm. Before returning this page's index, we will update the ns variable. The value of ns is this first index plus 1. So ns becomes 2. This is one execution of the search operation. Now let's say another call to the search operation is made, this time with a required size of 25. In this second call, we start at this node and again repeat the same 2 steps. So as per the first step, we look at this node first. This node does not have the space that we want. So we look at its right sibling and then we go to its parent. This node here also does not have the space that we want. So now we go to this node's right sibling and then climb up to its parent. Now here, this node has the free space that we want. So the first step can stop. And now we can consider this as the root of the heap and perform the search. So as per the second step, the search would go something like this, right? So the algorithm will stop at this particular node. Before returning, again we'll update the ns variable to point to this second last node, which is at index 7. So that's how this round robin based search operation would work. Now we have a solid structure in place, but unfortunately this is not enough. And we need to introduce some more complexity to make this work at a scale of millions of pages. Here's what I mean. This Max-Heap has to reside on disk, and everything on disk is a 8 KB page in Postgres. So the heap that we just constructed has to go on disk in 8 KB pages. Now if we store it in a single page, we get at best a few thousand leaf nodes. And that's not good, because the whole reason we want free space maps is to handle the scale of millions of pages. To achieve this scale, we have to extend this Max-Heap to a page level structure. This might be a bit nuanced, but bear with me for a minute. Instead of having one heap, we are going to split the heap in several pages. We will organize these FSM pages as a tree. Each FSM page will have a Max-Heap similar to what we just saw. The leaf nodes of these FSM pages, they are going to point to the child pages. So note that even though we have small heaps across these pages, as a whole, they form one big heap. At the last level of these pages, the leaf nodes correspond to the actual free spaces for the data pages. For instance, this 0th leaf node here has a value of 25, which means that the 0th data page of this table has the free space of 25. And all the other internal nodes will contain the maximum from the children. So that's the interpretation for these values. In other words, we have a tree of FSM pages, and inside each such FSM page, we have a Max-Heap. Now, because of this additional complexity, the search method also has to change a bit. Whenever the search method is called, we are going to traverse this page tree from top to bottom. And as we traverse these pages, within each page that we read, we are going to do the round robin based search. So that means each of the pages here is going to get its own next slot variable. Let's take an example for this. Let's say that a call to the search method comes in with a required size of 60 bytes. We will first read this root FSM page from disk into memory. Now in that page, we have this Max-Heap. We do the round robin based search in this Max-Heap, and it's going to give us a pointer to the page on this next level. So let's say the round robin search yields this first page. So we are now going to read this page from disk into memory. And again, we'll do the round robin based search on the Max-Heap of this page. Again, it will yield a pointer to the page on this last level. And let's say it returns a pointer to this page on the last level. So we again read this page from disk into memory, do a round robin based search here. And since this is the last level, whatever this returns, we return that to the caller of the search method. Note that for every search, we are going to read from disk exactly 3 FSM pages. One is this root page, then there is one page from this middle level, and there is one page from this last level. So think about the scale implications of this data structure. With just 3 levels, we can store the free spaces for roughly a few billion pages. Even then, there are some optimizations that Postgres does to push this number even higher. I'll mention these in the description of the video. But the bottom line is that to search for a page to insert a record, we have to only read 3 FSM pages. So even if your table has a billion pages, just by reading these 3 FSM pages, Postgres can figure out where to place the insert. And that's super awesome. To summarize, whenever we want to insert a record in Postgres, we first check the root of the FSM to see if there is any page that has enough free space. If there is no such page, then we immediately create a new empty page. But if there is such a page, then we traverse the FSM page tree and use the round robin based search to quickly find a page to insert the record. Let's quickly go to the terminal and briefly see how we can inspect the free space maps. I have split the terminal into 2 panes so that it's easier for us to run PSQL commands and the file system commands side by side. The file system is on the left and the PSQL is on the right. Let's first change to the dummy database. And let's now create a table in this database. Now, if we want to see where these FSM files are stored on disk, we need to know the path to those in the file system. There's an environment variable called pgdata, which is the directory where Postgres stores all its files. Let's change into this directory and list its contents. Now in this pgdata directory, we need to find the path to files of our items table. We can do this by using the pg relation file path system catalog. This tells us the file names for the items table that we just created. This means that in the pgdata directory, we need to change to the base directory. 16438 is the subdirectory which contains all the tables for our dummy database. In that subdirectory, there will be files starting with the prefix of 16489. These will be the data files or the FSM files. Let's verify this by changing into this 16438 directory and listing its contents. Currently, this is an empty table. There is only one file which is of size 0 bytes. This is the empty data file. We don't see the FSM file yet. That's because Postgres is lazy when creating FSM files. It won't create a file until it's required to do so. Similarly, it won't create FSM pages until it's required to do so. Let me clear both the panes. Now let's insert some dummy 200 rows of data. Now if we run the same ls command as before, now we see an additional file here. Now this is the FSM file. It is suffixed with the suffix _FSM. What do we expect this FSM file to contain? Remember that the FSM is structured in 3 page levels. So that means in this FSM file, there would be a root page, then there would be a child page of the root, And lastly, there would be the child of this child, which will be the page on the last level. So we expect to see three pages in this FSM file: the root, the child of the root, and the child of the child. We can do a sanity check by checking the size of this file. So the size of the FSM file is listed as 24 KB. So it has three pages. This is an important point. The FSM pages are laid out on disk in a depth first manner. So if a new FSM page is to be created here, that will be the second page in the last level, and it will continue in this depth first manner. In this particular video, we are not going to read raw bytes from disk for these FSM pages, but you can imagine that there will be some headers for the FSM page followed by the actual heap data, right? Instead, we are going to use a Postgres extension that allows us to inspect the details in the free space map pages. We no longer need this file system pane, so let me just exit out of it and let me clear this. Now let's create the PG free space map extension. This extension exposes some functions that we can use to inspect the free space map. Now let's use a function from this extension to list all the pages and their free space. Here we see that the table has a total of 6 pages, and of these 6 pages, the first 5 pages seem to have only 128 bytes of free space available, whereas the last page is full. Right now, all the pages are pretty full. Let's now delete half the rows and see how things change. We have now deleted 100 rows. If we check the free space again, nothing seems to have changed. This is where again Postgres is kind of lazy. Postgres doesn't update the free spaces immediately after the rows are deleted. The deleted rows are only marked as deleted, and their free space is claimed by a background process called vacuum. If we want to see the free spaces change, we need to call vacuum ourselves. And now again, if we run the free space command, we see that all the pages are now roughly half empty. As we insert more data, more of the data pages will be created. Correspondingly, the free space map will also be updated periodically by a background process. So that's it. That's how Postgres uses the free space maps to make inserts fast. I'll link the relevant files from the source code in the description and the Docker file and the commands for the terminal also. I hope you found this interesting, and I'll see you in the next video.